Hello everyone. So today we'll solve two more problems from Irodov. Okay. Now today I've written down the problems already, so I'll just read it out and I'll explain it to you as well simultaneously. So in this problem, I have a solid body which rotates with a constant angular velocity omega naught about the horizontal axis AB. So let me draw this part first. So since we are talking about a horizontal axis, uh, I can say that the axis lies in the xy plane. Okay, so let's say this is my x-axis, this is my y-axis, and let's say this is my z-axis. Okay, all right, and let's say this is my body. Okay, so this body at one point of time, let's say at t equal to 0, was rotating along this horizontal axis with an angular velocity given as omega naught equal to 0.1 radian per second. Okay, now let me see what else has been given about this problem. So at t equal to 0, the axis AB starts turning about the vertical with an angular acceleration of beta naught, which is given to me as 0.10 radian per second square. I need to find out the angular velocity and the angular acceleration of the body at t equal to 3.5 second. Okay. Now in the second statement, it has been said that this body also starts rotating about the z-axis with an angular acceleration given by beta naught, okay, as 0.10 radian per second square. Okay. Now this beta naught is the angular acceleration along the z-axis, okay, which means this body is actually having an angular acceleration in this direction. Okay, in this direction. By the right hand thumb rule, you know that this angular acceleration will have a direction. It will be along the z-axis. Okay, and this omega naught is actually turning the body like this. Therefore, the direction of the angular velocity is along the horizontal direction. Okay. Okay. Let me revert back. All right. Now, given this information, I need to find out the angular velocity at time t equal to 3.5. Okay. Now I know that the angular velocity along the horizontal direction, it is changing. It is changing. Why? Because this body also has got an angular acceleration along the vertical direction, okay, which means that it has an angular its angular velocity is changing in the horizontal direction as well, okay, but its magnitude is going to remain constant. Okay, so its magnitude is going to remain constant, which is going to be equal to omega naught. Okay, and its direction is going to keep on changing, which means that this body is going to have an angular acceleration along the horizontal direction as well. Okay, all right, I'll explain to you this particular statement a bit more clearly later on, okay, in the second part of the problem. Right now I just need to focus on finding out the angular velocity at t equal to 3.5 seconds. So I know that the angular velocity would be equal to omega naught at a particular direction along the horizontal axis. The angular velocity along the vertical axis, okay, this is going to change. It is changing because this body has an angular acceleration along the vertical axis, which is given to me as beta naught, okay, and at time t, its angular velocity will be equal to beta naught into t. Okay. Now these two vector quantities, they are perpendicular to each other, right? This is lying on the horizontal plane. Its direction is continuously changing, but at any point of time it will be along the horizontal, it will be on the horizontal plane only. Whereas this angular velocity is along the z-axis, okay? Which means that these two values are perpendicular, these two vectors are perpendicular to each other. So in order to find out the resultant angular velocity, I just need to find use the Pythagoras theorem in order to find out the resultant. So omega resultant will be equal to root over omega naught square plus beta naught t whole square. Okay, if you put in the value of omega naught, beta naught and t as 3.5, you'll get omega resultant as 0.1 square plus 0.1 into 3.5, that would be equal to 0.35 whole square, this entire thing to the power 1 by 2. If you calculate it a bit more, you will find out the value of the resultant as 0.6 radian per second. So this is the first part of the problem. Okay, now let us focus on the second part of the problem. Okay, in the second part of the problem, we need to find out the resultant acceleration. Okay, I know that the resultant angular acceleration, I know that the angular acceleration along the z-axis is fixed, constant, okay, given to me as beta naught. But if I kind of focus on the angular velocity along in the horizontal plane, I find that its direction is continuously changing, right? At one point of time, the body would be like this. At second point of time, the body would be at a different position, right? It would be something like this. At this point also, at this point also, this body will have an angular velocity whose magnitude will be equal to omega naught along the horizontal direction, okay? But if you see, the direction of the angular velocity in the horizontal plane will change again, okay? So at this position, the angular velocity along in the horizontal direction would be along this direction, right? Initially it was along this direction. After some time it is along this direction, okay? So we see that it is continuously changing because this body is rotating about the vertical axis as well with an angular acceleration of beta naught, okay? Now this angular acceleration is constant along the z-axis, but since my angular velocity's direction is changing in the horizontal plane, this body is also going to have an angular acceleration in the horizontal plane as well, okay? An angular acceleration which is perpendicular to basically the angular acceleration along the z-axis, okay? Okay, how do I find that out? So basically, if I think about it in terms of words, okay, let's say initially my angular velocity is in this direction, and after some time, let's say dt, my angular velocity is along this direction, and in this time, let's say the vector turned by an angle d theta, okay? Now this turn is actually a measure of the change in vector, right? Because the magnitude is constant but the direction is changing. So if I try to quantify the change in the angular velocity, it will be proportional to the small angular displacement that this angular velocity has taken in the small time dt, okay? So what we would be doing would be, we would essentially be writing down an equation based on our hypothesis. Okay, so in small time dt, the angular velocity changed by an angle d theta. Okay, so I would say the change in the angular velocity, which can be written as d omega, it will be proportional to d theta, but we can write down the proportionality constant as omega naught. Okay, it will be omega naught, because higher the value of omega naught, higher will be the angular acceleration, right? So we can say that it's kind of a proportional constant only. Okay, proportionality constant, sorry. So omega naught into d theta. Okay, now what is d theta? D theta would be nothing else but omega t, that is the angular velocity at any time t along the z axis, right? Because this body, because it had an angular acceleration beta naught along the z axis, it will have an angular velocity at any time t along the z axis. Okay, so basically at time t, this body would be rotating about the z axis with an angular velocity of omega t at any time t. Okay, that is what I've written here, that multiplied by dt. This will be d theta. Okay, let me rub this off. Okay, so this gives me d omega by dt as omega naught into omega t. Now omega t can be written as beta naught into t, right? Where beta naught is the angular acceleration along the z axis, omega t is the angular velocity along the z axis at time t. Okay, now it will have a direction, it will obviously be in the horizontal plane, right? Now since it is in the horizontal plane and this particular angular acceleration is in the vertical plane, I can find out the resultant by just using the Pythagoras theorem, basically finding out the resultant between two vectors which are perpendicular to each other. So let's say this is beta naught and this would be omega naught into beta naught into t. This is going to be the resultant. So the resultant will be equal to beta naught square plus omega naught square beta naught square t square. Okay, this to the power 1 by 2. If I take out beta naught from the root, I'll get the final angular acceleration as beta naught into square root of 1 plus omega naught square t square. Okay, if I put in the value of beta naught as 0.1, omega naught as 0.1 and t as 3.5, I'll get my answer as 1 plus 0.35 whole square. It will be nearly equal to 0.2, I guess. Yeah, 0.2 radian per second square. Okay, this is what my answer is going to be. Okay, so it's an interesting question. We just had to write down an equation based on words. We basically had to describe the angular acceleration in this case. By the way, the horizontal angular acceleration will always be perpendicular to my horizontal angular velocity. Okay, so the angular acceleration will be in this direction. Okay, alright, and this is just the horizontal angular acceleration. Okay, and which essentially is turning which essentially is changing the direction of the horizontal angular velocity as well. Okay, alright, this was my first problem. Now let us move on to the second problem. I have written that as well. So in this problem I have an aerostat of mass m, and it starts coming down with constant acceleration of omega. I need to determine the mass that needs to be dumped for the aerostat to reach an upward acceleration of the same magnitude. Okay, so before we start with the problem, we just need to define what an aerostat is. So aerostat is essentially a body which moves in the air. You must have heard about this aircraft called Giant Hindenburg, which used to fly over Germany. Okay, it was made by the Germans, and there is a lightweight gas like helium or hydrogen. So back in 1940s, the Zeppelin Hindenburg, it actually got burst. Okay, so it used to be very big in size, about 2 to 3 football fields in size, and it got burst and it came down on Earth within a few seconds. Okay, so post that, I think the production of Zeppelin Hindenburg got stopped. If you open Resnick Halliday, I think in one of the chapters they have this photograph of that Hindenburg bursting. Okay, so basically it's a body. It's a body. It's like an aircraft. Okay, it floats on the air. It has buoyancy. Okay, it has an upward force. Okay, and this upward force is because of very light gas. In this problem, we need to neglect the air drag. Okay, so in the first part of the problem, it has been said that this aerostat had mass m. Okay, and given this information, it was moving down with an angular velocity equal to w. I need to find out this weight that needs to be thrown off. Okay, from this craft, this aerostat, which will lead to the motion in such a way that it has an upward acceleration of omega. Okay, so in both the cases my buoyant force is going to be the same. Let's say in this case its mass is m dash. Okay, so we just need to write down the force equations in both the scenarios, and we need to find out m minus m dash essentially, because this is my initial mass and this is my final mass, and if I subtract the initial mass from the final mass, sorry, if I subtract the final mass from the initial mass, I get the mass that needs to be shed. Okay, so from here I can write down one equation, that is mg, that is the force downwards. Okay, minus f. Why? Because this buoyant force is in the upward direction. This is going to be m into w. This is my equation 1. From the second free body diagram, it's not actually a free body diagram. If I want to draw a free body diagram, I'll have to mention the forces, all the forces. So m dash c acting downwards, f acting upwards. Here the force acting downwards is mg. Okay, and based on this FBD, this my acceleration in the downward direction, this my acceleration in the upward direction. Based on this FBD, I've written this equation, and based on this FBD, I'll write down one more equation. In this case, I'll consider the upward direction as the positive direction. So all the forces that are in the upward direction will have positive in front of them. So F will be positive. Mg is in m dash g is in downward direction. So I'll write m dash into g. This should be equal to the mass of the aerostat times the acceleration. This is the net force acting in the upward direction, omega. This is my second equation. Okay, so from here I think I can eliminate f, right? If I just add these two equations, what do I get? I get m minus m dash into g equal to m plus m dash into omega. From here I just need to find out my m dash. Okay, m minus m dash divided by m plus m dash equal to omega by g. Okay, what do I do now? This implies I think I should solve for m dash straight away from this equation only. So I'll cancel this off. I'll write down my m dash as m into g minus omega divided by g plus omega. Okay, which implies m minus m dash is equal to m minus m dash is g into m into g minus omega divided by g plus omega. Okay, I just need to solve for this. I'll get 2 times m into omega, okay, divided by g plus omega. This is going to be my m minus m dash. Okay, yeah, so this is the total mass that needs to be shed by this aerostat for it to move in the upward direction with an acceleration equal to omega. Alright, this is what my problem was. These were the two problems that I solved today. We'll come up with more problems in later classes. Alright, bye.